and welcome to this 8th installment of our webinar series on geology and the mining sector. Today we are diving in lesson 2 of the third block, which will cover mineral resources. As usual, if you have any questions during this webinar, feel free to write them in the chat box on the right-hand side of your screen. We'll keep a tab of them and address all of them at the end of the webinar. If you do have extra questions while watching a replay, make sure you send them via email at info@iddpnql.ca. We'll pass that information to Francine. She'll provide us an insightful answer, and we'll get that back to you as soon as possible. Without further ado, Francine, the floor is yours.
Thank you. So I'm going to share my screen. Here. So welcome to lesson 2 of block 3. Mineral resource. Mineral resource will be separated into 5 big blocks. So what is a mineral deposit? A mineral deposit formation process, or mineral deposit classification, the ore mineral deposit geological models, and finally the ore mineral deposit exploration. So what is a mineral deposit? The technical definition of a mineral deposit is a naturally occurring, inorganic, homogeneous, solid with a definite chemical composition and an ordered atomic arrangement. A mineral is a substance that is either a single element, like gold, Au on the periodic table, a compound of elements, so like salt, composed of NaCl, a main component of a rock, like we've seen in previous lessons. Rock is composed of several minerals, like example here, granite is mainly composed of quartz and feldspar. So a variety of natural resources taken from the Earth's crust belong within 3 main categories of mineral deposits. We have the metallic, which can include gold, copper, zinc. The non-metallic, like talc, limestone, sand. These will be briefly discussed in this lesson. And finally, we have the fossil fuels or the energy minerals, like oil, natural gas, and coal, which is not discussed in this lesson. Basic mineral resource terms that are practical to know. We've covered most of them within the previous lessons. So the last 2 that I think we should go over are the aggregates, which is a rock or mineral material used separately as a filler in cement, asphalt, plaster, and other materials. And basically the alloys. Alloys are a substance having a metallic properties and composed of 2 or more chemical elements, of which at least one is a metal. The other element, metal, ore, and rock, we've covered before. And at the end, I'll show you, I've included a dictionary for mineral terms that has been done by the Geological Survey of Canada. So where and how do mineral deposits occur? So that's to answer this big question, we have to go back within our lessons. So I'm just doing a little overview. Everything in geology is based on our rock cycle and on our plate tectonics. So both rock cycle and the plate tectonics are the 2 geological cycles which determine how mineral deposits are formed and where they are formed. So mineral deposits occur in various tectonic and geological settings and activity. Some mineral deposits may be formed in one place, but be transported to another geographic location as a result of a tectonic force or any other geological process that would deform the original deposit. The study of tectonic processes and regional geology is important in understanding the distribution of mineral deposits. So for example, gold can be concentrated with other minerals in a vein that forms in a fracture, in a fractured rock, deep underground, and the tectonic process will help us to understand its source and how and where it was transported. So, just bringing back the famous rock cycle, where everything in geology is based on that cycle, and the plate tectonics. So we had seen there was four types of plate tectonics, or four types of plate boundaries. We have the divergent, convergent, transform, and the plate boundary zones themselves. Divergence are the one where we have new crust generated and where they pull away from each other. The convergent are the ones where crust is destroyed and one plate dives under another, like a subduction zone. And then we have the transform boundaries where crust is neither produced nor destroyed, and the plates are slide horizontally past each other. The plate boundary zones is boundaries which is not well defined, and the effects on the plate interactions themselves are unclear. So that was the image we've seen in previous lessons, where we have the convergent plate boundary, the transform plate sliding horizontally, the divergent plates pulling apart, and the convergent plates, one sliding under the other like a subduction zone. So within these plates, we have five types of different volcanism: the stratovolcano, the shield volcano, the seafloor volcanism, and the composite of stratovolcano and the volcano rift. Within these geological different environment systems, we have learned where we can find different types of mineral deposits. And these is going to follow us through this lesson, and it's very useful being on the field and knowing in which environment we are standing on and what was the past history of the geological environment to know exactly what kind of mineral deposits we can find within an area. We'll come back to this at the end, but we'll see mainly the main mineral deposits we'll see today are the epithermal, porphyry, magmatic, VMS, the gold veins, and the MVT and SEDEX deposits. So zooming in within a regional geological area, wherever we are standing, we know which kind of deposits we can find. Can find is the term to use because even if we are in the right environment, it does not mean that there is still a mineral deposit or existed a mineral deposit. So the orogenic gold, porphyry, copper, molybdenite, the epithermal gold, porphyry, copper, gold, the IOCJ, and the VMS are have their own geological environment to be found. This slide and the next one resumes exactly the 6 criteria we need to have within an area to be able to form a mineral deposit. So this is known as the mineral deposit formation process. And the mineral deposit formation process needs exactly these 6 components. It needs to have energy within the area, energy either from a deeper magmatic source, intrusion source. We need to have the ligand source, so the chemical favorable, favorable elements, the metal source, and the transporting fluid system. So any type of canalizing fractures, difference in porosities, faults, folds that can help to trap within an area any that will form or force the precipitation of metal to form a mineral deposit. Within the area of the trap, there will also be an area we call the deposit hollow. So it is an area where we have an alteration halo which is formed around our mineral deposit and which gives the indications, geochemical indications, um, to the geologist that he is near or far from a possible discovery or known model. So the scale here is also important to know what we are looking for. And finally, we need a zone of what we call fluid discharge, meaning when the fluids that were transporting rich metal got trapped, precipitated the metals, the fluids have to get out of the system, which is our fluid discharge outflow zone. So areas of much larger mass flux and energy systems are needed. Critical processes that must occur to form deposits are shown here. The identification of mineralization processes have to be interpreted at all scales, and it is not restricted to particular geological settings and deposit type. This is like these criterias are needed to any type of mineral deposit. If we push this figure within what we've seen so far within our lessons, especially for the mappable criteria, which belong to the cartography survey, and everything that we observe in space on the field or from our core, it will give us the criteria needed to know if each of these components are observed, existing or not. So when we are in the field, any observation that will show deformation, metamorphism, magmatism will give us hints of a source of energy or heat within the area. Anything that we can geochemically find corresponding to brines, magmatic fluids, meteoric fluids, will give us the ligand source within the area. Any enrichment within our source rocks from magmatic fluids will give us our metal source. Any observed structures of any kind or permeable or porosity difference within different lithological units will give us our canalizing uh, tunnels or transporting method of our fluids. Structural chemical traps of any kind and topological differences within the field can also be observed as our trapping systems. And finally, our structures are also our structures aquifers for the fluid discharges. For spatial proxies used when we are querying all these observations and defining targets, what we use for the energy source is anything that shows us metamorphic grades, igneous intrusions, differences in sedimentary thicknesses. We also have, for the ligand source, everything that relates to evaporites, organics, and isotopes. Any anomalies such as the radiometric, geochemical, and whole rock geochemistry can give us metal sources. Structural observations such as fault, shear zones, folds, geophysical and geochemical anomalies, alteration are all used for our transporting fluid canalizations. Dilatational traps, reactive rocks, again, geophysical and geochemical anomalies and alteration are used to search for our trap zones. And finally, any magnetic, radiometric, geochemical anomalies, and alteration structures are used to find our fluid discharge zones. Metal ores are classified and they are to be just before going on into the mineral deposit classification, we just have to understand that metal ores are naturally occurring materials that can be profitably mined. If there is no profit that can be done, it cannot be mined. When a rock has a high concentration of one mineral as compared to the other minerals forming the rock, it is called an ore. Whether or not a mineral deposit is considered an ore depends on its chemical composition, the percentage of extractable metal, and the current market value of the metal. We may find a high concentrated ore on the field, but if the market value is down, no one will want to invest and develop the mine. Metallic ore deposits can originate by crystal settling in igneous intrusions from hydrothermal fluids, cooling in pores and fractures, by chemical precipitation in surface or groundwater, or by river sedimentation called placers. The mechanism responsible for concentrating the valuable ore substance within a mineral deposit is separated into 6 main processes, and these are hydrothermal. Hydrothermal are the ones that canalize hydrothermal fluids. We have the magmatic process, which includes mainly the pegmatite and the kimberlites, which are formed at deeper depths and at higher temperature ore forming processes. We have the sedimentary, in example, the bended iron deposits and evaporites. We have the placers, which are mainly low temperature ore forming processes at the surface. We have finally the residual and the metamorphic processes. So just a little, before we go in detail, just a little image or schema for each. So here are the hydrothermal deposits. What we need to understand is that they are canalizing from any fractures they can find, and fluids are circulating like convecting zones within the area above a magmatic chambers and up to the water from the ocean. Magmatic are deeper, forming from ultramafic rocks, and have higher density minerals like iron, chromite, and the P.Geo sets. The sedimentary are the ones that are related within shallow areas and either under the sea or on the ocean crust or within the continental crust. We have the placer and the residual. The placer ones are the ones that naturally correspond to the natural dropping of material that is along the topographical terrain and within streams bottoms. The placer are the ones that were responsible for the well-known Klondike era for gold search. Here is a picture so that you understand the difference between gold within a rock, which is contained within a rock, and the placer gold, which is the nuggety style of gold that is panned within a stream or a river. So if we start for the hydrothermal deposit process, the concentration of minerals is by hot fluids circulating through fractures and rock pore or cavities, and heats up close to any hot igneous bodies and or at great depths naturally heated by geothermal gradients. Hot groundwater circulation dissolves valuable minerals passing through large volume of rocks, and as the hot fluid circulates in cooler areas of the crust, the dissolved minerals precipitates within favorable natural traps. So if we see this in image, We have the three central conditions for their formation. We have a highly active enrichment of fluids. We have suitable pathways, either cracks, fissures, faults, a difference of porosities for their migration through the rocks, as we see here. And we have favorable physical chemical environments for their deposition to take place. So right above our magmatic chambers, the hydrothermal fluids will circulate through whatever pathways they can find. And when it has the right geochemistry favorability, it will precipitate, and when it can be trapped within an area, it will precipitate the metal minerals and creating our deposit. Possible ways where we have hydrothermal deposits between an intrusion pluton, as we can see here, and the contact between sediments, sedimentary beds. So the trap would be the difference between both rocks hardness, both rocks rheology, and both rocks difference in porosity. Sedimentary rocks have greater porosity, so we'll be able to trap this fluid and force the concentration of these minerals. The hydrothermal veins from the fractures above of our magmatic chamber, passing through our less hard rocks, like here are sediments, and higher porosity rocks, so we would canalize through these fissures or weaknesses and would be able to precipitate within the fractures and or the veins. So we have here another kind which is disseminated ore, because we don't have enough to say that it is either within a vein, it is not within a vein, it is just disseminated as the word says, and is not enough concentration to say that it is massive as here. To be massive, it has to be considered to be above 80% of the sulfur. Semi-massive is between 50 and 75, 80%, and then below would be either disseminated or within vein or whatever texture needed, but it will not be considered as a massive or semi-massive sulfide. And of course, we have above the hot springs within the ocean crust. Examples here of our magmatic chambers with the hot magmatic fluids coming out from the cracks between both rocks and forming here within where the hydrothermal mineral deposit would circulate and would form our sulfurs. And here is from the fumaroles from our ocean crust. Good example here also showing the magmatic hot molten fluids circulating. Wherever it is circulating, it is picking up the geochemistry of the rocks it is going through, and this will help pick up any minerals and help precipitate within traps a metallic mineral deposit when we have the right physical chemical environment. So that's the right thing also to understand today. Even if we have the pathways, we need to be within the right physical chemical environment for our trapping to take the precipitation of our minerals. Example here of hydrothermal veins, veins of gold. So veins are like the smaller amount of minerals in the rock are called veins. They cross-cut our host rock. When we have a larger amount of minerals within the rock, they are called lodes, so lodes of gold. We have lodes of gold within our rock. If we go through the magmatic deposits, so we have our original magmatic chamber, So they form when minerals in liquid. So they're liquid, they're hot, they're molten, and in gas zones. They are forced upwards through any cavities, any fissures, any faults. They are forced upwards towards the Earth's surface, and they concentrate within a body of igneous rock by magmatic process. So once they redeposit and reform smaller chambers, these could trap along the way. They could have taken some metals going through different kinds of rocks, and when they have a favorable physical physical geochemistry, they will precipitate and form the mineral deposits. Like the sedimentation process, within these new magmatic chambers, the crystals settle based on their density. So the denser or the higher weight crystals will settle at the bottom of a magmatic chamber. So this is a natural zonation also that is done within the magmatic chamber. So the magmatic process, such as partial melting, fractional crystallization, and crystal settling in a magma chamber, it basically concentrates the ore minerals containing the valuable metals by taking the elements and concentrating them in minerals that separate from the magma, as seen here. So at the bottom, again, of a any new magmatic chamber, we have a zonation of these crystals. As the minerals crystallize from a magma body, the heavy minerals may sink at the bottom of the newer magma chamber. So the denser the minerals like chromite or magnetite, they will concentrate at the bottom of the chamber. So when we sample on the field and we have samples richer in magnetite or chromite or iron, we know exactly where we are within our magmatic chamber. So the magmatic deposits here from intrusive igneous and batholites, we see these molten hot fluids going up, forming a new magmatic chamber, and within these magmatic chamber will be maybe a new deposit depending on the material that was taken through the canalizing fluids. One of these well-known magmatic deposits in Quebec is within the Chibougamau area, which is called the Doré Lake Complex. It is a vanadium deposit. It is basically layered intrusions hosting a large deposit of vanadium, iron, titan deposit. On the field, we have this spectacular outcrops showing the different bending here. The darker bands are our magnetic rich bands, and the others are iron and titan vanadium. So if we look at this, it was studied, and we see the interval of the massive magnetic. So massive meaning these bands, the blacker bands, are 100% magnetic. They can vary from 60 to 100 meters thick, and the zone was calculated to have basically 26 million tons of magnetic with up to 1.47% weight percentage of vanadium oxides. Another well-known of these magmatic deposits is within the Southern Africa Bushveld igneous complex. So we have here a sample showing an olivine chromate-rich ore, and we have the bended outcrop on the field. If we move on to the sedimentary deposits, basically minerals concentrate by chemical precipitation from lake or seawater. The minerals deposit from the chemical sedimentation where the minerals precipitate directly out of water. So, of course, they will also respect the trend of our sedimentary host rocks. If we have bedded horizons, our deposits will be stratiform and bedded within these horizons. The minerals are found in beds or layer for the sedimentary rocks. So how this process is done is that the beds and the layers are formed due to deposition as seen here. And as this material is deposited, it will naturally sediment at the bottom of the water body. So there will be an accumulation. There will be a new bed on top, and these concentrations will be trapped within an area. And if the geochemistry of these trapped new material is rich with metals and favorable geochemistry to precipitate a mineral deposit, it will be formed within this area. A good example here is for the banded iron formations. Here we can see alternating layers of magnetic, which is the darker zones, hematite, and the schist, hematite, which is in the redder, and the schist in the grayish units. So here the iron-rich water is reacting basically with oxygen that was released from the alga, causing the oxidation of the iron. We also have within the sedimentary deposits gold-bearing conglomerates. Conglomerates are rocks, sedimentary rocks that are formed by rock fragments of one source or many source and a matrix. Rock fragments within a matrix automatically shows that the rock has a porosity. The porosity of the rock within contact with an intrusion rock will cause a higher porosity, and one of the nicest traps you can have to have the gold precipitation that was brought in by the canalizing fractures within the area. Two other major sedimentary deposits known are the either zinc, could be zinc, lead, or lead zinc deposits known as the Sidex and the Mississippi Valley Top. We have one in between that is like a hybrid between Sidex and Mississippi Valley type, which is known as the Irish type, would be like in the middle between the two. Sidex, meaning sedimentary exhalative deposits, are one of the several types of sediment-hosted lead zinc deposits. They are mainly within the ventral distal parts of these deposits within the seafloor, while MVT, the Mississippi Valley type deposits, are mainly within carbonate platforms and associated to carbonate rocks. So if we have sedimentary deposits, our Sidex here is a good example of coming from the folded layers, sulfides from the Sullivan mine in Abitibi. So what we see here is the rich accumulations of lead, zinc, and silver, which is found in the ore minerals, the sphalerite, which is the zinc sulfide, and the galena, which is our lead sulfide, which is deposited between thin layers of marine sand, silt, and mud in sedimentary basins as the clearer horizons that we see here. So the main ones in the world are the Mount Isa in Australia, the Red Dog in Alaska, and the Sullivan Mine. Sullivan Mine in Canada was discovered over 100 years ago in the Abitibi area. And it is the largest Sidex deposit in Canada, which produced 116 million tons of zinc at 5.8% zinc and 6.7% lead. Its other type, the Mississippi Valley, which is associated with carbonate rocks, you can see the composition of the rock is completely different. The carbonate rocks here is the creamy and light brown bands, and we can see it's our sphalerite, but because of the source, the color is completely different. The textures are completely different, mainly with the coliform texture. Coliform texture is the color texture we see undulating here. We also have the evaporites within the sedimentary deposits. Evaporites are formed by within an arid regions where there is an evaporation of our element. The main evaporites that can form in arid regions are the gypsum, potash salt, and our sodium salt. We also have within the sedimentary deposits the stalactites and stalagmites within the caverns. So the stalactites are the ones coming from the top with the T, and the stalagmites are the ones that are mounting from the bottom, the M. So the type of formation that hangs from the ceiling of caves, hot springs, or man-made structures, such as bridges and mines, are called stalactites. And the type of rock formation that rises from the floor of a cave due to the accumulation of material deposited on the floor from the ceiling drippings, it is basically composed of calcium carbonate. So the evaporation drop by drop of the calcium carbonate, it, it also can be composed of lava, mud, peat, pitch, sand, but each drop dropping on the other is gradually forming these structures. The placer deposits the mineral concentrations by flowing surface waters deposit high density minerals in streams or along coastlines. So wherever there are, again, natural traps along the water flowing, as the water is flowing in a regular current, when these material that is floating within the water current are trapped either by the natural change in topography, and there is a precipitation of the denser minerals which are getting trapped and forming these natural placer deposits. The main ones that can form are gold, silver, tin, and platinum. These are kind of natural traps that can occur in our terrains that can block or trap the uh, the minerals within our streams, and the deposits form from the dense minerals within the water. So we can either have traps behind rock bars and rock holes within the bottom of the stream, within a drastic change or fold within our bottom, and meandric loops within our river, and the prevailing change in the current within an area. So any natural trap is a good trap for placer deposits. Example here of a type of placer deposit, which is the alluvial. It's where materials such as soil or weathered rock particles deposit by a river or a flowing water. Some of these minerals are obtained by placer deposits called alluvial deposits in sands of valley floors and base of hills, as the next picture will show. Our placer deposits can be divided into four types: the alluvial placers, the aeolian, alluvial, and the beach. Alluvial are the ones that form by gravity found along the foothills. The aeolian placers are the ones formed and sorting carried out by the wind. The alluvial placers are the ones formed and transported by running water, such as streams and rivers. And finally, the beach placers are the ones that formed by the waves along water bodies like seas, lakes, and oceans. And these have an economic value. So this is the picture that would resume the placer deposits type. We have our residual placer, Using the gravity, some of these material will fall here. We have forming the alluvial placer, and then following some of the gravity again, we have terrace placer, and down within the stream, we have our stream placer. Residual minerals formed after decomposition of surface rocks. It's essentially what it says. It's a superficial process that form mineral deposits. So it forms by weathering enrichments, by mechanical concentrations, and by low temperature precipitation. So it's mainly due to decomposition and removal. Residual mass of weathered material is left that contains the ores. We have another kind of residual deposit, which is a biological deposit. Mainly chalks and limestones are formed by that process, which is basically calcium carbonate shells of organisms that are being brought by natural waves of an ocean body. The fossil fuels are formed from organic matter built up compressed in an anaerobic conditions. The difference here is to understand is that oxygen is present within the aerobic environment versus the anaerobic, where free oxygen is not possible. And the last mineral classification process is the metamorphic deposits. We've seen that before, maybe not understanding its crucial importance for metal deposits, but here this picture resumes it well. We have intrusion here, plutonic rock, and the contact metamorphism between our intrusion and the host rock, which is here in this example, sedimentary rocks. The contact between the two is what we call forms a metamorphism contact zone due to both difference between the lithology, difference between the hardness of each rock, the difference between the geochemistry of each rock, the difference between the porosity of each rock. So this will create also a zone of fissure, weakness, change in porosity, hence fluids going through, picking up any different kinds of geochemistry, metals, and then being trapped in areas, and if the chemistry is good, precipitating and forming an ore mineral. So pre-existing rocks and minerals of economic value undergo metamorphic changes due to great pressure and heat. Marble deposits form from limestones, slate deposits form from shales, and refractory minerals like kyanite, sedimentate, and andesite form from metamorphism. Just to make sure that we understand what an ore is, an ore deposit model is a conceptual and or empirical standard embodying both the descriptive features of the deposit type and an explanation of these features in terms of geological process. So whatever information we get from the field is known as the raw data, the uninterpreted data. Once we process that data and we start to interpret it, we transform it into the empirical and conceptual data that are used to interpret and understand the geological processes within an area. And these will help us find the different ores or mineral deposits within an area. And just here to repeat, an ore is a mineral or aggregate of minerals which can be mined, so extracted and processed at a profit. The distribution within the world of the major gold producers within the countries, different countries and continents. the world record highs between 2019 and 2020 for the productions of gold. Gold within Canada and the major other metallic mineral deposit possible within the country. So we see the gold is our reversed yellow triangle within the Quebec and Ontario frontier. We can see that these are mainly within the sub-province of the Abitibi, within the Superior Province. And we see the distributions of the other metals such as nickel, copper, iron, zinc, lead, the uranium, gold, silver, platinum groups, diamonds, coal, potash, salt, gypsum, tar sands, and the asbestos. So mainly within our Abitibi area, we have gold and copper. Within, if we zoom in within the Abitibi greenstone belt, comprising both Quebec and Ontario, we can see in the yellow contours the main gold deposit location, and we can see where they are focused. Three things we can see right away without even going on the field, that these are mainly situated locally, physically, wherever we have main structure or main structural deformation zones, which is the dotted lines, where we have a drastic change in geological lithology, either between sedimentary and volcanic rocks, or sedimentary and volcanic and intrusive rocks. So we have our heat sources within the intrusions here. We have our canalizing zones, which are our major faults, and we have our difference in geochemistry and difference also in rock lithological geometry forming natural traps for these fluids. Within the greenstone belt, we can see here also the main deposits and where they stand within the 20 of them stand within the world-class type of deposits. 75% of gold from Abitibi is within these classes. So if we go for examples now for gold deposits, for the orogenic types within fractures, as we see here, we see a nice vein of gold within a rock. How we would go for exploration, for drilling, as we've seen in the last lesson for drilling, we always try to plan drillings that will pass through perpendicular of our known mineralized zone. This is a surface image. So if we have our lens and the orientations of our lens and the displacements of our mineralized zones, we try to place and deviate our drill holes to make sure they go through each of these lands and give us the most information possible to define the geometry and the orientation of our gold zones. If we are within a fold hinge, where we can have a thickening of our rocks and of our mineral deposit, we try to implement several orientations of our drill holes to make sure we get the entire thickness or thickening of our mineralized envelope, and to be able to define its geometry as precise as possible. Example here of orogenic lenses, their discontinuity are defined and more and understood once we add more drill holes. If we go through now the base metal deposit, the VMS, the volcanic massive sulfide sulfide VMS are mainly within tectonic settings, which are right above our magmatic deeper chambers. So the convection's fluids, circulation of these fluids will pick up through its circulation different kinds of minerals, metallic minerals such as iron, copper, zinc, and lead, and circulate until it has its favorability environment, traps, and so on. This is a classical VMS. If we cut it right in the core of a VMS, this was defined by Franklin in 1996, which is the guru of VMS deposit. And this shows exactly where we stand when we sample a deposit, and it shows us if we are in the deeper portion of the core of the deposit, if we are moving upwards more to the surface, if we are in distal surface areas versus distal deeper areas. It also implies with the different kinds of alteration pipes that we have within the difference between the alterations if we move on from sericitic to chloritic versus just chloritic heart. We know if we are within the distal or proximal area of our stockwork zone. Stockwork is just a word from the German language showing that instead of having just one vein or one fracture, we have a network of fractures or veins or fractures within the core area of our VMS. As we move upward, we see also ozonation of our metals going from chalcopyrite to pyrite to pyrrhotite, moving upwards to pyrite, sphalerite, galena, and finishing with sphalerite, galena, pyrite, and barite. So that too shows us where we are in depth, and also the stratigraphy of our metallic bands shows us if we are within the higher region or more superficial region towards the core area. When we are within the proximal area of a VMS, it is richer in chalcopyrite or hence copper. And when we move farther away, it is richer in zinc or sphalerite. When we are within the distal or superficial part, it is mainly what we call our exolite horizon, which is the silica, pyrite, and hematite. So this is a guide any geologist will use from any observations on the field and observations also back from the lab, from the alteration and the geochemistry to know exactly where we are within our VMS. This also from Franklin is another graphic which is defined for our metal distributions within our VMS, because we can have copper, lead, zinc, and this graphic along with the concentrations of our elements will show us in which type of VMS are we in and its original environment. So if we are within richer lead, zinc zones, we are within the SEDEX VMS, which are sedimentary origin. If we are more within our zinc and zinc copper, we are within our VMS deposits, which is a volcanic origin. We can have hybrids between zinc and copper along this line, and we can also have hybrids from zinc, lead, and copper mineral deposits. On the field, this is a typical massive sulfide VMS where we have massive pyrite and massive sphalerite. So When we say massive again, it's just a percentage of our sulfur, and it has to be higher than 80% of our rock. So from underground, we have our pyrite and sphalerite horizons. From a core sample, we have our pyrite, sphalerite, massive sulfides horizon. You can see that the main rock, original rock, is less than 20% of what is left. Another good example here of a VMS with our sphalerite and pyrite. Where are the VMS within the Abitibi Greenstone Belt? Well, they are shown here in our red squares, and we have the hybrid half red, half yellow, and we have the load gold. So basically within the Rouen-Noranda area are our richer gold VMS. They are metal VMS, but we also have our gold VMS. And then we have like a separation of them. We have between Rouen and Val d'Or, we have like a segregation of gold VMS. These belong to the Bousquet-La Ronde area. And then we have a segregation, a separation, either gold or VMS, copper, zinc, plus or minus gold and silver. Within the Matagami area, we have our VMS, rich in zinc. Shibugame area is more metallic but still has some gold, and in between we have a sparsity of a little bit of both. This is interesting too because it will show within each area of our VMS within the Abitibi Greenstone Belt the concentration of zinc, copper, and lead. So we can see that in the Rouen-Noranda area, which is known as the copper capital, our VMS are richer in copper. Richer in copper meaning they are closer to their source. We have within the Val d'Or area, which is almost half and half. The Bousquet area is richer in our zinc VMS and has some gold, which is not shown here. The Matagami VMS is mainly zinc. And then we have around the Urbain-Barry area, which is mostly zinc too. Joutel is half-half, and the Chibougamau area is mainly copper. If we go back within the latest, a few years ago, around the Matagami area, the latest discovery is the Bracemac-McLeod deposit. We have a section here, and it's just to show our main VMS lands with the importance of knowing the alteration halo around the deposit. So the darker gray shows a strong chloritization, as the lighter gray shows ceratization. So if we are within the ceratization, we know that we are farther away from our main deposit, which the halo around has to be richer in chloritization. So how this little lens here that was found within our key two-fight, which is a felsic volcanic unit, and a zoom of this area, how the drill holes were put in to define the precision of the geometry of that lens. Also, where this lens was already curved or folded, we need to add on as many drill holes as possible every time we have a drastic change in orientation. So it would be important to place a new one here to make sure we cover this drastic change in orientation. And as seen in the last lesson, it is also as important to add drill holes even if we don't have within our zone to make sure that this non-continuity is well proven with hard raw data and it is not just interpreted. So if we move on now with the porphyry deposit, we have here their location within the map area, the world map area, basically under big volcanoes, so basically under big subduction zones. So where you have the thickest red lines here, here, and along here. So that means basically where we have copper, gold, molybdenite magmas, hydration melting at deeper zones within subduction zones area. So meaning also at deeper depth and higher temperature, warmer, heater temperatures. This is a perfect example also to understand that while at deeper depths we can have porphyry, copper, silver, molybdenite deposits, if we move higher, we can have different types of deposits. So that's an important thing to understand. So from the beginning of this lesson, I've been talking about to know where are we standing and the evidence we can find on the field to know if we are close to the surface, intermediate depths, or deeper depths, depending on our observations, geological informations, and the geochemistry we investigate. So this is a schematic porphyry system showing that in the root of an andesitic stratovolcano, it has mineral zonation. The deepest zone hosts the porphyry deposits. So as we see here. Intermediate zone will host both precious metal and base metal veins and replacements. So as we've seen right away. So these could be within breccias, within faults, and so on. And the shallow zones, the epithermal deposits, host mainly what we call the precious metal deposits, so the gold, silver, arsenic deposits. Porphyry deposits within the world area, so the main ones out west in the country, out west in the States, and along the Cordilleran ends of the South America. We have the eastern side of Australia along the subduction here of the Indonesian, Malaysia, and the southern portion of eastern Europe with Russia. Within the country, our major porphyry deposits are within the western area. We have a few within the rest of the country, but the major ones are out west. So here is an example with the alteration in textures with the both metals, bornite and chalcopyrite for copper. We have the types of alterations we can find, so phyllic and potassic, as seen here. Potassic is not always seen with the eye, so we use a process called staining, and these, once we apply that on the rock, wherever we see the color coming out, we know that it is a potassic alteration. So here we see the potassic alteration within a granite, which is the pinkish area, cut by quartz veins that contains molybdenite. Again, in this, how do we drill porphyry copper deposits? One, the drill holes have to be deeper, since the deposits are deeper. And we also have to use different orientation drill holes to be able to determine more precisely, again, our mineralized zone and to cover all its continuity and its lateral and depth extents. The epithermal deposits are separated into two, the low sulfidation and the high sulfidation. So you have the low sulfidation in yellow and the high sulfidation in red, and you have their distribution within the world map. Thermal deposits are shallow depths. Within the country, we have their distribution. We have a few in Quebec, Ontario, within the Abitibi area, but we have most of them within the western part of the country. These epithermal systems, as seen here, is a good example also to see above of porphyry stock or porphyry copper mineralization, which is formed at depth. As we go higher, we have our epithermal high sulfidation, and then on the lateral extents, we have our low sulfidation veins, and we have our change also in the alteration, which is important to note here, from potassic alteration associated with the porphyry coppers, with the sericitic alteration associated here with our high sulfidation, and our low sulfidation chloritic alteration covered with our argillic alteration at shallow depths. Example here of a epithermal low sulfidation system on the field. And our gold silver ore here, I did it on purpose to show an example of an alloy meaning an assemblage of more than one metallic. So here we have our gold and silver, which is within our quartz vein that we see here in white. We have our alloy of gold silver, which is cross-cutting a sericitic altered and pyrite altered volcanic rock as our host rock. How do we drill how do we drill epithermal systems? Basically, knowing that there are epithermal systems, we know that we can plan shallow depth drill holes with a few that go a little bit deeper to make sure that we cover the natural terrain of the area. We're moving on now to the magmatic nickel copper PGE. PGE is the platinum group elements within the world, so the known ones. And in Canada, the well-known one is in the Sudbury area in Ontario. So these are the locations within the country. In Quebec, the known one is within the northern portion of the province in the Raglan area. So when we have minerals like pyrite, no, but like pentlatite is composed of a iron nickel sulfide. So we know that we are automatically close to a magmatic nickel copper PGA or area. Within the Sudbury example we show here, Sudbury example was basically formed from a meteorite impact. The meteorite impact had two roles: the heat, the impact between the rock and the surrounding caused the heat and the breaking of the rock, so the weakness and the traps and the canalizing of the fluids, causing the texture which is known as shatter cones, as seen here. So these shatter cones as seen here, and this is one of the biggest in the country. Within the field, the unlapping fallback breccia The granular impact of showing an impact of the melting, and how these deposits are drilled, again being several kinds of lens, not always continuous. We have to make sure that our drill holes are modified to make sure that they are covering each of the lithologies, going through perpendicularly and covering all the area systematically. So along an area, we can decide to make equidistance drill holes, but it is important also to refine areas where there is a natural change in topography and natural change in the um, mineral deposit envelope geometry and shape, to make sure that each drill holes give us the information to refine its shape and orientation. If we move on to the mineral resources from marine source, so from the oceans, uh, it is what we call now our new mineral frontier. We have both the oceans and outer space, but for today I chose oceans. So, because we have more exploration done in the oceans right now than the outer space. So the seawater contains abundant dissolved minerals, and many are useful elements, but most extraction techniques that are currently used are energy intensive and very expensive. So that's one reason why there is not a lot of exploration in the ocean right now. The hydrothermal ore deposits along seafloor spreading ridges are a possible source of many materials, but currently they are too deep with our techniques. So this also limits the explorations of the area. And finally, the manganese nodules, which are widely distributed on the ocean floors, is a promising solution, but right now, there are still too many political, environmental, and legal obstacles that must be overcome before they can be mined. So these marine mineral resources are known along the mid-Atlantic ridge as the TAG model, so the transatlantic geotraverse. They basically have the same shape and characteristics as our Earth VMS. And this, as shown here, is if we take one and we cut it in the middle, in the core. The only difference is that we would see from the ground what we call our black smokers coming out from the vents. So we have in the proximal core area our copper footwall stockwork stringer zone, which has a silicified pyritic stockwork with the chloritized hematized basalt. And we have gradational contacts between the two. When we move up, we have our massive copper. If we move to a distal area, we have our lead zinc massive sulfides. To the lateral extents of it, we have iron massive sulfides, and we have the BIF, the bended iron sulfides. As shown as the VMS, the TAG model is the same, as exception with the vents as we see here, with the black smoker, which are rich in sulfides, and with these collapsed chimneys. So the black smokers are vents that regularly push out all this material rich in metals, and if they are able to be trapped somewhere, they will form a mineral deposit. So a lot of the marine mineral resource explorations helped understanding the VMS deposits that we see on Earth, because down under the oceans, we could see the process of these venting and the process of these metallic circulations fluids and how they would be treated. So an example here, we'll see a video later on. And we have them with like the convection zones within the seafloor. Typical black smoker's chimney expulsing metal-rich copper zinc sulfides. An example here of these rocks, rich in pyrites, fallarite, and chalcopyrite within an anorite. This we'll see a bit later on. And the other phenomenon is the one that forms the precipitation on of substance from seawater on the seafloor, which is a very slow process. And the example here is the manganese nodules. If we move on a little bit, little bracket for the industrial mineral deposits, this could be a completely different lesson. But the most important industrial mineral deposits are known as the sand and gravel, the crushed rock, silica sands, the clay minerals, the salt, and the phosphate. For the non-metallic resource, not mined to extract metals or a source of energy, they are used for either construction materials, such as sand, gravel, stone, limestone, and gypsum. They can also be used for fertilizers containing components like phosphate, nitrate, and potassium for the agriculture area. We have all the industrial minerals, non-metallic minerals such as rock salt, sulfur, asbestos. We have everything that has to do with gemstones and jewelry, like diamonds, rubies, etc. And we have everything that has to do or used for the manufacture industry, for either household and business products like glass sand, fluorite, diatomite, and the graphite. These are examples of limestone quarries, the potassium minings out west, and the pegmatic that are formed at deeper depths, slow processes, hence forming big, gigantic minerals, crystals, such as emeralds that are gemstone-like. So to complete a bit this part is to understand this figure resumes all the other lessons we had so far and how they are useful for geologists to move on within an area and be able to explore for ore mineral deposits. So it is not magic. It all comes from the geologist observations on the field, underground, from the cores. So a geologist will use all the geological maps to identify the favorable rocks and structures before going on the field. We'll look for rocks altered by fluids. We'll look for chemically altered rocks. We'll also look for difference in drastic contacts between two different ecologies with different orientations, with folds that could cause some traps as shown here, with any fractures, fissures, difference in porosity, difference in rock rheology, major faults, any anomalies that can show buried ores that cannot be seen on the surface, either by geophysical anomalies. So a geologist is like a detective that will use all its observations to reconstruct an area's geological history and try to discover new mineral deposits. So it is basically just a reconstruction of the geological history of the area and just using his or her observations to make, hide, or destroy deposits. So some of the observations can also say, well, no, in this area, I cannot find any deposit. I have nothing, no observations, so nothing going on for me to know that I will be able to find a deposit. If I move on to this area, I can see that I start to have several elements favorable to have the formation of a possible mineral deposit. This is like the summary of all that we've seen today. This is our figure that we use all the time, depending on which type of mineral deposit we are searching for and where we are on the field, where we are at depth. If we are working at the surface, we're searching for paleoplacers. If we are moving down to deeper depths, what kind of formation, if we are working with sedimentary rocks versus porphyry versus magmatic chambers versus high sulfidation to low sulfidation and so on. So this graphic or schematic illustration will show us exactly where, in which environment, we can find an ore mineral deposit and which type can be found within this specific environment. So this schematic illustration shows the various types of gold deposits, including gold-rich volcanic massive sulfide shown at their inferred crustal level formation. This one here is listing all the different criteria that can be observed either on the field, from the lab samples, from the core, from underground, and characterizing them with their importance if we are looking for the source, the active pathways, the physical throttle, the trap where the mineral deposit will precipitate, and the preservation of these based on, as we've seen in other lessons, in which scale are we working at? What are we looking for? Are we working for to determine the ore shoot? Are we working at a deposit scale, regional scale, camp scale, or prospect scale? And this is an example for the orogenic gold system. The same application, but this time for gold VMS. And this time we are including everything. Everything from the scale, from the timing. Are we before the VMS formation, after the VMS formation? Are we within a VMS environment, a gold, silver rich VMS environment? Are we within lode gold? What kind of processes, what are we seeing on the field to give us hints of what kind of processes are we working in? Which kind of metal formation process are we witnessing, and so on. So the graphic summary here of all the different possible controls on gold, silver enrichment in VMS systems that operate on different spatial and temporal scales are basically based on all the observations we can have. So all the details we can see on the field, we need to understand them as key processes. Each observation gives us a key to understand the process that was going on in a sector. It helps us identify main features of our mineral deposit. It helps us improve the genetic models we interpret within an area, and it helps us define queries based on the type of ore exploration. So again, if we go back to all the lessons we've seen so far, everything we pick up on the field, either from the geology surveys, the cartography, the structural information from the field, the airborne surveys, the gravity surveys. I could have added everything that has to do with sampling, geochemistry, and so on. Is called primary data. Primary data is everything that has to do with data picked up on the field, underground, from our rock samples, and primary data is observations that are not yet interpreted. Once we have all these information, we sit down and we try to process them one by one, and these will create empirical data. Empirical data is absolutely interpreted. So this can vary from one person to another, but if the observations are well taken down, they uh, they will resemble from several interpretations if they are well precise. So once we know where we have our main structural geology, we can create distance to faults maps as seen here. We can create strike to nearest faults to known deposits to know which orientations are favorable. Once we have a solid geology from the surface and understand it well, we can create what we call the rheological contrast between our different rock units. So the rheological contrast will show the difference between the different units, rock hardness, rock rheology, hence maybe the rock's porosity, and so on. We can also, with the geochemistry, make geochemical maps showing areas that have geochemical contrast, as seen here with the contrast with the iron, magnesium, and calcium content, and so on. And then we have what we call all the elements to be used and crossed and intersected with each other to form our more advanced interpretations, which then fall within conceptual data. Conceptual data is each geologist will sit down and create favorable potential maps. And the favorable potential maps, like here, the examples are for the favorable host rock lithologies where we think we have the most chances to have the formation of an ore mineral. So this will pinpoint out the main areas and leaving out the other areas. Then we can have favorable lithological contact types, so where we have abrupt changes from intrusions to sediments to felsic rocks, we can calculate the distance to these, and then we can have distance to major favorable tectonic environments, and using each of them, we can intersect these elements and finally use them to define our mineral exploration targeting areas to plan our future drill holes. So this is a schematic diagram just resuming everything we've seen so far with the difference in environments, if we are in VMS, which scale we are, if we are in the upper crust, lower crust, depending on which temperature we are working in, the temperature will be seen within the geochemical metamorphized minerals we can observe on the field, the alteration we can observe on the field, and so on. So all this again is giving us the different geochemical mineral or depositions that are possible and what kind of mineral deposit can be found on the field. So here what I've put is the examples from 1 to 6 of main types that are known. So the M.Sc.A Creek type deposit at 1. The 2 is the Rainy Rivers and volcanic ore gold deposit here. At 3, we have the around the gold-rich VMS types like Bousquet, Magami, and La Ronde Pena area in Abitibi. We have the Lemoine area from Chibougamau here in 4, and the Horn and Camel style or rich VMS from Rouen-Noranda area here in 5, and 6, we have the typical Noranda type VMS deposits. Just to show, if we do a schema, how they might be alike with their content, but really different from the environment where they were formed. So that's something very important to understand before even setting foot out on the field. Finally, I just wanted to finish before showing the videos, the conservation of mineral resource, because our need in resources ever always growing, and we need to reduce this expansion. So possible ways in being able to reduce this expansion would be to try to substitute some of these mineral resources. So examples here would be how in the last years plastic was mainly used to replace metallic automobile parts. Recycling has been very important and done more and more during the past years, where many metals are now successfully very well recycled. Uh, but we need more recycling, and we need to understand that it's not easy to recycle all the metals. Measures to reduce the demand must be the key, but it's not hard, since we are always on an ongoing evolution and development in the world. So the more we're going to go, the more we're going to need resource. Example of recycling, so just using materials. We're just melting some of the scrap metals and glass and crushing some of the used concrete. Substitution could be also another good thing to do. Over the years, the pipes that were used, plumbing pipes, went from lead to copper to now plastic pipes. We now use also a lot of optic fibers instead of the copper for our telecommunications. So here, before going to the videos, I just wanted to show, I placed a link for the glossary of mining terminology that was done with the Indian and Northern Affairs in Canada. Here is the link to go live within the dictionary or terminology, and this is the English PDF document that you can download from the site. So I'm just going to move out of my PowerPoint. For the, I've placed a recall of the plate tectonics that I will not show this week. This week I just wanted to finish so you could understand well what is an ore, how the minerals are concentrated within the different geological environments, and we'll finish off with a nice video showing live areas around black smokers. So starting with the first video, what is an ore? We're going to go a little bit over that.
Unless you have some form of telepathy, you are probably reading this lesson on an electronic device. That electronic device and its associated battery contain any number of metals in its circuitry and components, and those metals all began their life as an ore. An ore is a special type of rock that contains a large enough amount of a particular mineral, usually a metal, to make it economically practical to extract that mineral from the surrounding rock. Not all minerals are found in a large enough amount in one location to make it worth it to remove the ore from the rock through a process known as mining. Ores can be mined in a number of ways, including strip mining, as shown here at this uranium mine. If there is a large enough amount present, the rock will be extracted and processed in a variety of ways, depending on the type of the material, to remove the mineral from the surrounding rock. Once they are extracted and processed, the minerals can be turned into whatever products are desired, including the components in your cell phones and computers. One of the best known metals, gold, is extracted from gold ore like this sample. Ores are classified based on how they form. Some ores form from the cooling and crystallization of minerals within magmas, lavas, or igneous intrusions. These are known as magmatic or volcanic ores. Nickel, copper, and iron ores are typically formed from magmatic or volcanic-related deposits. Carbonate alkaline ores are formed from other igneous processes other than volcanic and activity. Rare earth element ores and also some diamonds are part of the carbonate alkaline group. As you can imagine, if ores can form from igneous processes, then they can also form from metamorphic or sedimentary processes also. Metamorphic ores often contain lead, zinc, and silver, as well as some iron oxides. Sedimentary ore deposits included banded iron formations and gold, platinum, zinc, tin, and even diamond-containing ores that formed in sedimentary environments. Lastly, ores can form as a result of hydrothermal processes. These processes involve the exposure of rocks and minerals to extremely hot water, usually near oceanic hydrothermal vents or hot springs. Most of the world's gold ores, as well as uranium ores, formed from hydrothermal processes. So what are some uses for ore? All ores contain a large enough amount of a particular metal to be economically viable to mine the ore and extract the metal from it. Because of the large amounts of metal contained in ores, the uses for ores are essentially only limited by humans' imaginations. Any use you can think of for a metal, whether it be in a cell phone battery or automobile part, or even a medicinal ingredient, is thus also a use for an ore. As human needs change and technology expands and changes, the uses for ores and their associated metals have increased markedly over the years. In recent years, electronic components have increased the demand for certain metals, including silicon and rare earth metals. Anything you can think of that in any way contains a metal can somehow be traced back to that metal's parent ore, so it really puts in perspective the importance of metal ores to life as we know it. Copper ores, like this one, are frequently processed into wiring and other electronic components. Ores are a special type of rock deposit that contain a large...
The next video will resume how the ore can concentrate within specific areas.
Imagine you're a detective trying to solve a missing person case. Your first moves will be to gather as much information as possible about the case. You will want to know the history of the person and the events leading up to the disappearance. In much the same way, when geologists are trying to track down specific mineral resources, they need to understand the history of the deposits and how they were formed. This knowledge allows us to make educated guesses on where to find valuable mineral resources. In normal rocks, valuable metals such as copper, gold, and silver are measured in parts per million or even parts per billion. For us to be able to extract these metals, we must find locations where the mineral resources have much higher concentrations. In this lesson, we're going to investigate 6 different methods that concentrate mineral resources on Earth. These methods are associated with igneous, sedimentary, and biological processes. You'll remember from other chapters in this course that igneous rocks are those that crystallize from liquid magma. Magma can also be responsible for concentrating some elements in minerals. There are three main igneous processes responsible for concentrating mineral resources: magmatic segregation, late-stage crystallization, and hydrothermal fluids. Minerals with high metal concentration are often more dense and thus accumulate at the bottom of a magma body. This process, called magmatic segregation, is responsible for forming several large layered intrusions which hold the majority of the world's chrome deposits. One of these layered intrusions is the Bushveld complex in South Africa, which is the most valuable mineral province in the world. The Bushveld holds a major portion of Earth's platinum, chromium, and vanadium resources and formed when crystals were settling out of a magma due to their high density. Late-stage crystallization occurs when rare elements do not easily fit into a mineral structure. So as magma is crystallizing, these elements will stay in the liquid phase for as long as possible. Once the magma is almost completely crystallized, only small pockets of liquid remain that are concentrated in elements including lithium, uranium, and beryllium, which will eventually be forced into rare crystals. These deposits are called pegmatites. Pegmatites are notable for containing large crystals and valuable gemstones such as topaz, tourmaline, emerald, and aquamarine. The final way that magmatic processes concentrate mineral resources is through hydrothermal fluids. These are hot fluids that are driven into pore spaces and fractures of surrounding rock as magma is intruded into the local bedrock. These fluids are concentrated in elements that are water-soluble or easily transported by water and can be valuable like gold, silver, copper, lead, and zinc. Hydrothermal fluids surrounding granitic magmas concentrated approximately half of the world's copper deposits. Let's concentrate now on sedimentary processes responsible for forming mineral deposits. The two main types of sedimentary mineral deposits are clastic deposits and chemical precipitates. Clastic deposits are formed when minerals and rocks are sorted by either density or size during transport. Mineral resources concentrated by running water are called placer deposits. Heavy substances such as gold ore require fast river currents to remain suspended in the flowing water. Where the river current is weak, these heavy substances will drop out of the water, forming placer deposits enriched in heavy minerals and rocks. Both gold and valuable gemstones, like diamonds and emeralds, can be concentrated in placer deposits. Many of you will be familiar with placer deposits because they were the source of the 19th century gold rushes along the west coast of North America. Mineral resources can also be formed via chemical precipitates, which are formed from chemical reactions involving water. The most valuable of these are the banded iron formations, which are alternating layers of iron-rich deposits in chert that formed approximately 2 billion years ago. Geologists believe that the Earth was once covered in more iron-rich rocks, which were eroded by surface water. In the water, the iron bonded with oxygen to form iron-rich mineral precipitates that collected on the bottom of the water. Today, we only have these dramatically colored ancient deposits to tell the story of their formation. The final method of mineral resource concentration addresses the formation of carbon-based resources, including coal, oil, and natural gas. Because they are so important to our modern economy, we could spend an entire course covering the formation and concentration of these resources. Coal, oil, and gas can all be traced back to ancient organic material that was buried under thick layers of sediments, subjecting them to high temperatures and pressure. Since coal was commonly formed from ancient swamps, you can locate coal along ancient shorelines. Oil and gas are trickier to locate because they are mobile within rocks. These resources will migrate into porous rocks called reservoir rocks that are surrounded by some impermeable barrier, such as a non-porous rock layer. Oil and gas deposits can commonly be found trapped beneath impermeable layers under folds or faults in the Earth's surface. As we have discussed, there are a number.
And the final video will be the one showing the environments within the black smokers and what the people are discovering new, what's going on around black smokers. And this, like I said, is like the new frontier for mineral ore exploration.
The Earth cracks open. Fluid and minerals spew from the seafloor. Water shimmers. Life abounds. We're looking at hydrothermal vents, originally discovered near the Galapagos Rift in 1977. Basically, a hydrothermal vent is a hot spring produced by underwater volcanoes or tectonic activity. But what's really cool about them is the abundance and assortment of life that exists there. It's not life like we're used to up here on the surface. It's adapted to the dark conditions of the deep ocean. Organisms that live around hydrothermal vents don't rely on sunlight and photosynthesis. Instead, bacteria and archaea use a process called chemosynthesis to convert minerals and other chemicals in the water into energy. This bacterium is the base of the vent community food web and supports hundreds of species of animals. What kinds of animals? Well, scientists on the NOAA ship Okeanos Explorer went to the rift in 2011. And here's just some of what they saw. Riftia tubeworms, also called giant tubeworms, which can grow to their full size of almost 5 feet long in less than 2 years. Bathymodilus deep sea mussels, which are often the first creatures to colonize the vent, and are able to survive for a short time after the vent is inactive. Serpulid, or feather duster worms, and Tevnia tubeworms, which are often the food of choice for vent crabs, the top predator of the vent community. But it's not all animals down there. Researchers also saw white flocculent material erupting from the vents like a snowblower, an indicator of microbial life beneath the seafloor. And of course, there were fresh lava flows, which means the seafloor is continuing to change. And that change means there's always more to learn.
Hydrothermal vents are found in isolated spots along the rift valleys of mid-ocean ridges, where seawater that has penetrated cracks in the crust has circulated down to the magma chambers, left salts behind in the cracks, and then risen to the surface, now superheated and filled with hydrogen sulfide gas from the magma chambers. En route to the surface, these hot fluids leach elements out of the ocean crust, elements like iron, copper, zinc, and even gold. When these fluids exit vents in the seafloor and mix with the cold water there, the metals get together with the sulfur, and sulfide minerals precipitate out, creating mineral deposits, much like mineral deposits left behind in your water pipes. These mineral deposits grow over time into large chimneys that extend above vents in the sea floor. As previously mentioned, the hydrogen sulfide acts as an energy source for the chemosynthetic bacteria that support an exotic food web and ecosystem that is located immediately around this vent. Giant tubeworms collect gardens of these chemosynthetic bacteria within their bodies. The tubeworms feast on the garden, and the garden is fertilized by the waste of the tubeworm, and receives gases as the tubeworms extend over the vent and soak up the hydrogen sulfide gases escaping. Both the bacteria and the tubeworms that act as their hosts are known as extremophiles because they can handle extreme temperatures. The vent fluids can be between 350 and 400 degrees Celsius. Other animals that live around vents feed on
And this is the last. So this ends our lesson. Coming back.
Hi again. So,
So this
lot
completes
to unpack once
yes.
again. very interesting. I think, well, congratulations to everyone that's been with us so far. That's our 8th installment, going 12. Just want to remind everyone that watches this starting next week. We'll see the next 4 installments on a weekly basis, contrary to every other week that the way it was previously. If you're watching a replay of this, it won't affect you. Everything's online, so feel free to breeze through all that content. Once again, if you have any questions regarding anything that you've seen so far, or specifically in this lesson, just send us an email at info@iddpnql.ca. We'll pass that information on to Francine, and we'll get that answer back to you as soon as possible. Until then, be safe, have fun, and we'll see you for the 9th installment.
Thank you.